All right, I guess we can get started then. Our speaker this week is Mudit Rai. He was Brian Battel's student at the University of Pittsburgh, and he just recently started at Texas A&M, postdoc there. And he's going to tell us about gravitational waves from Nnaturalness.
Thank you for inviting me. So today I will talk about this work that I did with Brian and our other postdocs at Pittsburgh. It's called Gravitational Waves from Nnaturalness. So just to give a brief motivation. So the idea of the naturalness in a simplistic way is that the EFT should not be extremely sensitive to the underlying UV physics. So as an example, in the case of the standard model Higgs, so the Higgs mass receives like one loop corrections from the tops and the other standard model fields running in the loop, and it is quadratically divergent to the scale of the physics which is going in. So naively, if you have quantum gravity coming at m Planck, around m Planck, it will scale as square of the m Planck square. So in our case, we are not really trying to address the big hierarchy problem, but let's assume that there is some other theory, let's say SUSY, which kind of brings the scale from m Planck to some cutoff lambda. So in our labs, we have seen that there is no new evidence of new physics at TeV scale. So suppose if there is some expectation of new physics entering at, let's say, order of 10 TeV, so then you want to address this little hierarchy issue, because as again, like the correction to the mass will scale as 10 TeV square, although like the MH is around 100 GeV. So we want to explain this little hierarchy, and that was the motivation for postulating this Nnaturalness model. So this is a model that was written down in 2016 by Arkani Hamid and his collaborators. So in the most basic setup, we have basically large n copies of the standard model, which have varying values of the Higgs mass parameter. And in this case, because the Higgs mass square can vary, so some of the sectors will have the Higgs mass parameter, which is closer to like our Higgs value, and it's parametrically smaller than cutoff. So, and I will show you like how we are doing this. And our standard model is identified with the sector having the smallest negative squared Higgs mass. And finally, in order to like populate the different sectors, we assume that there is some light reheaton field which can naturally transfer most of its energy after inflation to our standard model, and very small Flex energy to the other sectors. And we'll see how it works. And to be precise, for our setup, we consider capital N, which is the copies of the standard model, to be 10 to the 4, and that gives the cutoff scale to be around 10 TeV. So this is like our setup. Yeah.
What problem are you trying to solve here? Little hierarchy.
Yes.
So what's that, 10 to the minus 4?
Yeah, like this will be 10 to the minus 4-ish.
And you're introducing that, and they introduce a factor of 10 to the 4.
No, but this is just like if you have this many large copies, so your scale will go from like 10 to like that's 10 TeV, but you will also have some sectors which are lying around the Higgs value. So in a sense, like you have different sectors. You're like not just saying that you can only be near the cutoff, but you can also be near like 100 GeV or so in the mass square.
If you introduce 10,000 standard model.
Yeah, but like those of them, like the other copies will not get enough energy density.
I mean, are you putting in the solution to solve?
So in what sense?
Well, you put in a large number there.
Yes.
So you're trying to solve this, tuning one part in 10 to the 4. So
yeah, so maybe if you say it in that sense, it's more like kind of transferring the problem, but not exactly killing it. That's the, yeah.
Wait, is the tuning you're solving even 10 to the 4, or is it like you're bringing the Higgs mass from like 100 G to 10 G, 10 TeV? Then only 2 orders?
It's a square.
Oh, because it's the mass
square.
Yeah, it's a square.
Okay. Yeah.
10 to the minus 2 if you don't want it to look too bad. It's 10 to the minus 4 if you want it to look worse.
Okay.
Okay. Yeah, so just to give a more concrete model, so we have these n copies of the standard model, and then the I represent as like the numbering of that sector. So the MHI square, it goes from like minus lambda v square to lambda v square. And for our case, we choose a very like a simple approach in which we just take a linear distribution. So any ith copy gets it's basically scaling as like minus 88 square times 1 plus 2i by r. So and I equal to 0 is our standard model. And as you go I greater than 0, then it just becomes more and more negative mass. So those are like the standard model like sectors. And if you go in the other direction, so then there the Higgs mass square is positive, and those I will call as the exotic sectors.
So these masses are the masses at the weak scale,
Yeah, these are just like the bare quantities here, like
but
just
they're
like,
running, so they're the masses at the weak scale.
yeah, I think so. Yeah, I think that should be the case.
They all run in the same way, or?
Well, all of them are like the exactly same standard like copies, right? In that sector, it's just the same mechanism as like the I equal to 0. So you just like take different sectors and
So the index I runs over the copies just for the standards.
Yeah.
pardon? Yeah, I equal to 0 is us, then I equal to 1 is like the next sector, and then so on. And then I goes from 0 to n by 2.
Do they need to be linearly spaced?
No, like you can choose different scalings. This is like an easier, like this is like one way of choosing a distribution, but you can have, if you want like quadratic or even like log, like the results will actually depend on how you choose the scaling. But like we focused on like this specific way. So you can either like choose the scaling, and then also another ambiguity is like how you choose the reheaton. So in our case, we are choosing like a scalar reheaton field. So basically we introduce some scalar reheaton field which gets the energy density after the reheating from inflation. And the way we do it is like we are coupling it democratically to all the different sectors with a coupling A, and we assume it's some mass M5. But there are also cases in which you can think of the reheaton as a fermionic field, but we don't study that aspect. So right now we just say that there is a scalar reheaton field which couples democratically to all the sectors, and we will see that by this form, for at least the mass of the M5 to be between, let's say, 100 GeV to 300 GeV, it will automatically give the standard model the most energy.
So you said N5 has what, and that is gonna have the mass one, energy.
Between like, let's say 100-ish, like, so to get like the most energy through decay to the standard model, M5 will lie between, let's say 50 GeV to 300 GeV, like roughly.
But doesn't 5 get corrections?
Yeah, but A is also very small. Like A goes as like lambda over n. Yeah.
That's 10 to the minus 4.
So you couple to every case of the
Yeah, so I try to couple A with all
with
the,
the same strength?
yeah, with the same strength.
And what is M5? Oh, just to have an idea of what scale is M5?
So M5 is like roughly like 50 to 300. Like I will, so in my parameter space, I will show like M5 versus the scaling R. So, but like roughly, if you want to keep it in mind, it's like order 100-ish.
Sorry, other questions. So the physical mass of all these Higgses is what?
So these are like the bare masses, but like physically, I will calculate what the wave is, and then from there we can also calculate like the physical masses. So they will increase roughly as like our mass times square root I, approximately.
For half of them is the M squared with a different sign. So
Yeah,
there is no break, electroweak.
yeah.
Oh,
So-
okay, so they all,
Yeah, so half of them are like,
half of them are,
Yes, half of them are having positive M squared, right?
right.
So the radial mode is heavy,
Right.
but the
But the potential is on the other hand.
other modes are QCD scale mass.
yeah,
The potential is around the origin, there's still positive mass. Even though the regular symmetry, I mean, there's still be a mass.
There will be a master radial mode, and the other modes, as far as I recall, get the mass.
yeah. So like the half of the guys are very light. I will show.
But half of them are breaking symmetry as well, right?
Yeah, in their sector, half of them. In their sector, it's like,
Right.
it's like copy.
I understand. So you have many SU2 crusty ones.
Yeah, I will show in the next
But
photo.
and half of them
sorry.
are broken,
Yeah.
half of them are not broken.
Yes.
Okay.
Yeah, so like in the right, like in the half of those
But
sides.
this 5 couples.
Yeah,
all of them.
yeah, but A is small.
But, and you wouldn't see that?
No, so the point is like the A is extremely small.
Yeah. Huh? Yeah, early users. Okay. Go ahead, guys. I'm just wondering, because if 5 couples to all of the Higgses,
Yes,
then the Higgses themselves coupled to all the other Higgses.
Yes.
Is 5.
yes,
That would be small.
but it's extremely small.
Small, 10 to the minus 4 is not such
No, like A is much smaller. Like if
small. Not 10 to the minus 4?
no, it has to be like even smaller. Like I think like you make sure that so like when you look in the value of I didn't write on the value of A, but the idea is like any kind of like cosmology, like you will not see it anywhere other than the delta and effective. Like the coupling is so weak that the 2 sectors when they talk to each other, those like if you want to look into in the lab, you won't see it because the coupling is extremely small.
This A.
Yeah.
How small is A?
Because A is dimensionful as well. Right?
Yes.
Yeah, so basically what you are saying is like I want to calculate, let's say H, and then phi in between, and then H prime, H prime. Yeah, as an example. So that has like a square going in, right? And then A square and phi is like of the same order. So and basically if that one, like if you say it at least goes as some like suppression of n times some dimensional quantity, and assume like the scale of the power, like the mass scale is still of the order of the let's say the m phi. So even if it's like scaling as 1 over n, then there's like 1 over n square suppression. So it's like 10 to minus 8-ish times the dimension of the theory.
And the dimensional quantity is still the weak scale here?
I think that so it is like basically upper limit is lambda h, but like it can be smaller. So it need not be like v square, but so it is like basically A has to be less than lambda h over n. Yeah, I think, and you can like make it smaller and smaller. I don't know like what's the lowest reach you can go, but like as you make like, I think that the idea is that no matter what you do, like the amount of energy density that you dump into like the ith sector over the standard model, in that thing like the A square will cancel out. So A does like A will not change your like how your phi field dumps energy into different sectors, and that's like the physical thing. So you make it smaller, you evade the exponential bounds without changing like how the cosmological bounds will be affected. Pardon?
How's the standard model is selected with all the coupling stuff?
So you will see that because of the mass of the m phi, how far m phi is with respect to the standard model mass. If it is close by, then it will populate to standard model. But if you take m phi to be like larger, then the decay width will choose a different sector. So we just like calculate using like the decay width of the phi field to all the sectors, and then we can show that provided it is in the mass range of, let's say, order 100 GeV, then standard model is automatically getting the most energy density. So basically the gamma of standard model is like largest versus gamma I.
The other Higgses are like order the cutoff scale, they're massive.
Yes, no, I think like
You have to, but you mean the physical, which is what I asked earlier.
Yeah, like I know they're linearly spaced. How far apart are they linearly spaced?
so it's like basically scaling is like the wave of the I greater than 0 is basically scaling as like our V times square root of 2I by R plus 1.
What's off?
So R is like the scaling, it lies between 0 to 2. So it's like some order 1 value. And then I goes from like 0 to n by 2. So basically it's like scale as like V times square root I if you go in this direction, like the wave. And on this vector, because the Higgs mass is positive, So the symmetry breaking only happens due to QCD becoming strong. So that's why like here the wave is much smaller than, let's even say like lambda QCD of the ith sector. So here the VI is much smaller than even 100 MeV. Okay. So yeah, so just to go back to this thing. So we calculate that the ratio of the energy density of the ith sector over the Standard Model, which is approximately proportional to the decay width in the ith sector over the Standard Model, is like less than 1, and it is independent of the coupling A, and this is like less than lambda h over n, and we generally take it to be even smaller. But for our purposes, since the ratio cancels out, so we are like not really worried about what A is.
But you have very many.
Pardon?
You have very many of these sectors, right? You have to, the correct measure is like the sum of all.
Yeah. So when you take a sum, it actually becomes like log of n. So basically, like the ratio goes as like 1 over I. I will show in the next slide. So when you take a sum of 1 over I, that is like log n. So it's like only, it's like coming like the n enters like through log, not like linearly. So if like log n is like 10 to the 4, it only like n is 10 to the 4, that's like around 4-ish, and then outside factor will make it that it survives delta n effective, at least for some of the parameter space. Yeah, so like this cosmology is completely determined by m phi comma r, and it's like very weak dependence on capital N.
Still trying to understand what, so you have phi is the thing that survives after inflation.
Yes.
Now phi is gonna decay into all the other Higgses.
Yes.
And what happens, so for the standard model Higgs, that will decay or scatter and produce all the standard model particles.
Yeah.
What about all these other sectors?
Yeah, so I'll show you in the next slide, like just the decay part.
But you presumably now have energy density in all these other sectors, right?
Yes.
I think M phi is chosen so that you can change our Higgs.
What about
No, he has chosen a democratic structure for all sectors.
Yeah, but
I'm saying, but for the decay to be kinematically allowed, it won't decay to that level.
like it will decay, but only while like the scaling will proportionally scale as 1 over mhi square. So we will see that the decay rate, if you just calculate it, it scales as 1 over mhi square.
Is M phi lighter than the Standard Model?
It can be lighter or heavier, it doesn't matter. It just like mixes, right? Like it's kinematic, like it's like the mass mixes. So basically the decay scales as like theta I square, and theta I square goes as like 1 over mhi square.
But M phi has to be at least twice the Higgs mass, right? If it's gonna decay it.
But
No, it's like it's just like mixing, like the mass mixing the theta. It's like the Fi.
it also decays to Goldstone. That's what it's not just mixing.
So yeah, so it's like two. Sorry, maybe I can just like show you. So for the Standard Model like sectors, so I'm like partitioning the problem into like two halves. So the first part is like for the Standard Model like sectors, these are the relevant diagrams. So it's just like mixing with H, and then whatever H decays to, it can decay. And if you calculate just like this this diagram, so then this proportional, this basically scales as 1 over mhi square.
So phi is lighter than H?
Well, even if it's heavier, then it can directly like decay. If it's like it can heavier like 2 times, then it can just like decay directly. But if it's like lighter, then it can like decay like this.
So
But
in half of the sectors, the electric is not broken and the corresponding Goldstones are.
yeah, so in the other half, the decay is happening via loop. So I will show you like in the next slide how the decay is happening.
But H contains the Goldstone, no?
Yeah, so in the other half, like the way we calculate it is like we just phi, and then it's like a triangle of this H, and then the H can couple to something else. So basically, like every decay comes with a loop suppression.
I don't think so.
Uh,
Like it's not.
Why is it not massless? You don't know what.
100 MeV.
Why?
Because if the electroweak symmetry is not broken, it's broken only by QCD.
But there's a bare mass term that's big. Well, some of them, the MHR squares, some of them were negative, some were positive, but they're all of order 100 GeV. Right?
That doesn't matter there because these are complex fields, right? So they have one heavy field and three light fields, right? So that, like, if I take a Higgs mass of the star model to be large, right, it will decay to longitudinal doubling.
Yeah. So, but like, so let me just like maybe complete. Like first, I can show you this sector. This is like the usual standard like story. So here, like, if you just see that the like, I think here if you agree that the gamma goes as like 1/mhi square. They will just have to calculate like this. So the mixing is.
And that's coming because there's a bed for H. That's giving you the H5.
Yeah. So this is just the usual mixing.
So M5 is parametrically smaller than the scales.
I think I also take it like above. So like I will take, and then there like you will get some enhancement.
If it's above, then the 1/mh squared is irrelevant. 5 will decay to.
Yeah. So there I will.
Four fields of it, and I insist not one, 4 fields.
Yeah, but yeah, so you will see like when I show you the parameter space, whenever like the kinematical channel opens up, the delta and effective bounds can be evaded because it predominantly decays to the SAM model. Let's say if it's above 2W or 2H. But for rest of the cases, because like the next heavier guys, I'm never going into the phi, which is heavier than let's say 200 GeV.
The half of your fields doesn't have a valve to.
Yeah, so this part is not for the that section. I will show you like what the diagram there that we calculate.
But those sectors have light fields where which phi comes.
No, let's stick with this sector. He's gonna get the other sector in a minute, but so this sector, and now there are also these copies of all the fermions as well.
Yeah, it's like everything is like standard model like exact copy.
So you're gonna get 5,000 of these things.
Yeah. So but the point is like each one is scaling as 1/I. So when you take a sum to calculate this delta and effective, this is just like summation of 1/I. Then that just goes as a log.
I still don't understand that formula. The mixing, yes, it goes like that, but phi can counter decay directly to the goldstones of this H dagger H.
Even in the standard model sector.
I mean, like there are 4 fields in H dagger.
Yeah.
Well, suppose the Higgs is heavy. Well, can't you decay to the other 3? That's what I'm missing.
But H is real.
I think it would still decay if you put properly like, you know, I know the model where the S squared H dagger H and S is the say.
So let me.
The dark matter. And then you ask the question, how is it analyzed? And the analysis for 4 degrees, not in the heavy mass.
So, but like suppose if so here I selected like the reheating temperature to be 100 GeV. So all the standard model like sectors already have like they are already in there. Like the wave has already been there, and you are sitting like in that. Like once you expand your Higgs to the wave and then the excitation. So your W's and all the things have gotten a mass. And now what you are just saying is that in that case, your phi h square just becomes like a phi small h square, and you try to like do a mass mixing. So after that, like, I'm not sure, I will still, like my goldstones are still around. Like if the symmetry-breaking is already happened, like where are my goldstones? No, but like my reheating is always, like I'm choosing the reheating temperature to be between like less than the 246. So the reheating temperature is smaller, like the at least the standard sectors already have undergone the symmetry-breaking.
Log n is still a big number, right?
Yeah, so it's like I didn't write down the factor outside, but I will show that. Yeah, so the point is like when you see the parameter space, it's already.
Well, 4. I mean, but delta and effective.
Yeah, so it's around. Yeah. So when you see the parameter space, like most of the parameter space is kind of like already ruled out, but there can be regions which are still allowed. So it's not like, I should have like written a proportionality. So it's not exactly 4. There's some factor outside, which I didn't write. Yeah, but you will see, like, as you said, that most of the parameter space is kind of like ruled out just by the scaling.
Just to understand this 1/mh² formula.
Yeah.
So I understand if the Higgs is heavier than, like I have the Higgs mass showing up in the propagator of the Higgs in the denominator, but as the VEV is larger, don't the mixings also become larger? So I also get some numerator scaling with the Higgs mass.
Wait, how?
Like, doesn't the mixing between the phi and the Higgs depend on the VEV of the Higgs?
Yeah, that's in theta.
Yeah, it's like this
Yeah,
is.
yeah. So the heavier the Higgs is, the larger theta is.
No, this is just like the Yukawa, right? Like this interaction is just the Yukawa, and everything else is like mass in theta I square. So this has to go as like 1/.
That's from, must be from the diagonalization.
Yeah.
Because there's an off diagonal M phi, phi H mixing up, so then you have to put that in. That's gonna give you this theta.
Why is it, if it's through the mixing itself is 1/m². This is a mixing square. Theta I is proportional to 1/mh².
Yeah.
Why the rate?
So let me see if I've written out the formula. I think you do get like 1 power from there, but let me see. So I've written the formula. Yeah, so I think I have like not written out the formula here, but I think like naively, if you just calculate here, like this rate, so you are saying like there is no 1 power going up.
Well, your energy is set by the phi, the mass.
Yeah,
of the phi,
yeah.
right? So after you take into account the mixing angle, the Higgs intermediate Higgs mass is irrelevant. After that, it only enters in mixing angle. So I would say it's 1/mhi².
Well, but like naively, this coupling, like if I just think, like if I'm doing the calculation like that, like the way you are saying, then this is like why I yeah. So
That coupling contains mass of the fermion divided by.
yeah, so the mass of the fermion will be like y times v, right? And then the v is also scaling approximately as like mh. So you might, like, I think if you just like calculate this guy times this guy, like one of the power, like the power that you are saying, that roughly that should be like like the two powers should cancel out. Like this I just like calculated and get, I can like do the calculation later if you want. Yeah, so like, okay, so let's say if you believe that, I think like I checked that definitely this is like 1/mh², but I can show later. But if you believe that this is true, then basically this gamma scales as like 1/I. And if you just take a sum, then basically this is contributing to like logarithmically. For ith sector. So as you go higher and higher, like the energy density which you put in becomes smaller and smaller.
This is where you get the log.
Yeah, yeah. And once you sum them up. Okay, yeah. So for the case of the exotic sector, since there is like no symmetry breaking happening at heavier scale, and the symmetry breaking only happens at very small, like the QCD scale. So basically, you have to calculate diagrams which contains this H dagger H kind of like triangles. And in these cases, all the particles like W's, Z's, and the leptons, they are much lighter. So they are everything is like less than 100 MeV. So all the, like you have to calculate the decay width. And when you calculate this kind of diagrams, what you find is that the gamma I scales as like 1/mhi². So here the scaling goes as 1/I². So what it means is that in this exotic like sectors where there is no electroweak symmetry breaking, here as you go in like larger and larger I's, the separation becomes smaller and smaller. So basically you can just more or less just consider like I equal to -1, like the first exotic sector. and your delta n factor will more or less will be like approximately, this is the most dominant contribution. And in our in our setup, if your like MH -1 is like less than or equal to M5/2, then this also opens up some on-shell decays, so that can slightly enhance the decays of the phi. So we want the whole point is like we want to look at the phase transition in this sector. So we want to look into the parameter space where we can dump enough energy into this exotic sector, where we do not really violate the delta effective bounds, but still get some appreciable gravitational waves. So we will see later how that works.
Just again, if I forget about all the large I's,
Yeah.
but just think about I, so I equals 0 is the standard model, right?
Yes.
So I plus or minus 1.
Yeah.
If I think about just the I plus or minus 1, what's the branching ratio of phi to the I plus or minus 1?
So for the like the -1 here, it is going as like approximately as 1/mH⁴ in this sector.
No, but the branching ratio is gamma I over the gamma standard model
Yeah.
for the I equals plus or minus 1.
Yeah. So here, like I haven't taken out like the external the outside factor, but this roughly scales as like, so this guy goes as like 1/mH⁴ of that -1, and like the gamma, like the standard model, I can like calculate, but roughly it is like less than 1. Like it has to be less than 1. And you can show
It
it's
must
like,
be a lot less than 1, right?
yeah. I mean like, so
But why is it so much less than 1? Because the masses of the Higgses are almost the same. They only differ by this little r that you have, right?
yes.
So
But I think like, so for at least for this sector, like the decay, you have to pay a price of this loop as well, right?
okay.
So
But
that's
the other
why,
one you don't pay.
yeah, but the other one has at least like, so the I from let's say 0 to 1, like your mass went from let's say around 100-ish to like 400-ish, like if you 200, like 300 or 400-ish. So it is a jump, and like it will contribute like to the delta effective, but it's not like that it will, like there's no way you can have more
But
energy in
you
that
must know
sector.
what gamma 1 over gamma standard model is. Gamma plus 1, where I is plus 1.
Yeah.
Compared to, so gamma 1 over gamma 0. That was on your previous slide.
Yeah. So yeah, but I didn't write down, like I think he's asking for like the external factor, like the factor outside, like roughly it's,
Is it a 10th or is it 10 to the minus 4?
so I think like well it can't be like 10 to the -4. Like I'm not sure if it's like 10 to the -4. It is like, let's say 0.1 or 0.01. It can't be
Well,
-4.
0.1 is, it would be then excluded, right? Because
Yeah, so I think that's the point, is that most of the, like when you see the parameter space that I show you, like it's already like very small ranges are left. Basically like
it looks like it's order 1, right? It's
yeah. So it looks
order
like order 1, but it's like there is a, so if you just like look at the ratios, so I think this guy goes as like square root of 1 minus m4mh² over m5², and the denominator will also go as like square root of 1 minus 4mh0² over m5². So basically this ratio is going as like square root of m5² minus 4 times the mhi², which is scaling as like I. So you will approximately get like ratios of square root of, let's say, order like less than 1 over the square root, like order at less than 1. So this is like between order is like 0.01 to like 0.1. Like that is the only difference, because like everything else is same. It's just like the kinematical factor ratio, in which the ratio of the m5, the m4mh, like 2mh over m5 enters.
Well, you should go ahead, but I'm not really seeing why there's a big suppression for gamma 1 relative to.
But I think like, yeah, so I will say it's not like a very big suppression for the first sector. Like the first 2-3 sectors are important, and you will see that the only allowed parameter space, which is like really not constrained, is when your m5 is resonantly converting to our Higgs, because like this ratio theta, this is approximately is like 1 over m5² minus mh².
Theta 0 and theta 1 should be about the same as well.
So, but like in the case when your phi can resonantly convert to the Higgs, like when it's closer to the Higgs mass or like closer to the 2 times the W mass, that's where you will definitely beat anything else. Yeah, so you will see that those are the regions which are kind of like very open. Everything else is quite constrained. Yeah. Okay. So just to like show you pictorially how the scalings work. So on the y-axis is our rho I over the rho standard model and raised to 1/4. And I choose M5 to be like 100 GeV for this plot. So the blue curve, the blue line is for the standard model like sectors where it's like the usual electroweak symmetry-breaking happening. And the purple is like mh square greater than 0. So in the purple, the scaling was all the way is like minus half, I raised to minus half. For small i's, for the blue, as long as like the fermions are still lighter than the phi, then you can decay by the mass mixing. So the scaling was I raised to -4. And once you're like after some values of I, it's like large value of I, basically your fermions are now, every fermion is heavier than the phi. So there you have to go through loops, and that's why the scaling becomes same as what here we have.
I appreciate this structure for the blue line.
Yeah, so the blue line is like every bump you see is like one of the fermion is getting heavier than the phi. So you can't decay it directly. Like the 2 times m phi is now. M phi is like not greater than 2 mf for that bump. Because like the wave is changing, mass of phi is same. So as you get higher and higher in the higher sectors, the wave is so large that the mass of the fermion overwhelms the mass of the phi. So you can't directly decay to it. So like you have lesser and lesser options left to decay. So that's why like this, there is each bump. The first might be like the bottom and then the charm and then so on.
You only really care about I up to 10.
Yeah, like for us, we only care about like, because our I is actually less than n/2. But this was like, they also considered like in their original model. So this is, I just got like, want to get from the original model. So I think they wanted to consider different scenarios. So this is like some scenario is like n is very, very large. So they just wanted to show you like how it works.
Like if you want something big, higher.
Yeah. Like I think if your n is of the order of 10^18, but we don't touch that scenario. Yes, for us, it'll mostly be in this region.
Out of curiosity, why don't you try to do the big hierarchy? You're just
I think like we are like, we wanted to just like look at so the whole study is more or I just like, this is just for trying to get a picture of how Nnaturalness work. But like our idea was to just look at the first hidden sector, because there was like a possibility of a QCD like phase transition. And our motivation was from the gravitational wave side, because we were thinking that maybe it can cut into the region of the nanograph. So for the nanograph, generally expect the phase transitions if they happen in around MeV scale. So there's like, there was a hope that we can see if the gravitational waves which come, if it cuts through that region. So that was like our motive. This is just like a model to probe into it. Yeah. So, but we are like not really after the hierarchy problem per se. We're just like using the model.
I mean, would you still be able to do this if you took 10 to the 16?
I am not sure, because like then the delta infective bounds is very hard to get away. Like even for tensor-4, like you are seeing that the delta infective bounds are getting, yeah. So if you have this many, I think you need some other way of beating the delta infective.
And then what are you putting at 10 TeV? So you have a cutoff of 10 TeV.
Yeah, so we are assuming that like if some SUSY or something else is filling that gap, but we are not really focused of like how you do that. So yeah, so just to since I'm only focusing on this I equal to -1 space, they're going to show just a bit of the mass spectrum. So here, because like the quark, once like the coupling becomes larger and larger, so the formation of quark condensates, and this leads to like the spontaneous breaking of our electroweak symmetry because of this QQ bar.
So just
Yeah.
turning back. So when the Higgs mass is negative, or sorry, not like in our sector positive, you're stating that there are no tree-level decays of phi to gallstones.
Yeah.
They're not gallstones, right? So
Yeah, but there's no
each contains in principle 4 fields.
Yes.
So you're saying there is no tree-level decay to like the Higgs, the real component, the radial component,
Yeah.
is heavy. I agree with
Yes.
that. But there are also, H dagger H is a sum over 4 scalars, right?
Yes.
And you're saying that there is no decay over 5 to 3 other scalars. Any of the scalars.
Yeah, if I calculate if I go to the unitary.
So that I got the statement, right? So you're claiming that it occurs only at the loop level.
Yeah, if you say that, yeah.
Why?
Well,
Why there is no decay to because this is a case of unbroken symmetry in some sense.
no, but like for the standard, if I'm talking about the standard
The
model.
standard model, I understand.
Oh, okay, yeah. Here, sorry. I think if you are talking about this sector, everything is going.
Talking about the sector where the Higgs is not away from zero, that it's at zero, right?
Yeah.
And then there are 3 other scalars that are Goldstone.
Yes.
Oh, no.
Yeah, no, they're all heavy.
They all have, sorry, yes, they're all,
Yeah.
yeah, they're all happy, they're all happy, all happy, so, you're right, it's gonna be a loop.
Okay. Yeah. So going back, since I'm like more interested in this exotic sector, just to give a mass spectrum of this, how this exotic sector looks like. So once our coupling becomes larger and larger, and approximately at the temperature of around 85 MeV, that's where like the quark condensation happens, and it triggers the electroweak symmetry breaking in that sector. And roughly this condensate scales as like 4 pi f pi square. And then the Higgs is scaling as f pi square over the mh minus 1 square, f pi cube, sorry. And f pi is not very far, not very different from our f pi. So you can think of like roughly the order, and like all of like, you can think of this as like order 100 MeV each. So slightly smaller, but not very small. And then the 3 of the gold stones like W and Z, they are now getting the mass with scales as the f pi. So they are around order 10 MeV, and these are the heaviest guys in this spectrum. And then the other 32, they get their mass from the explicit symmetry breaking terms in terms of the UPawas. So all the pions lie between, let's say, a keV to MeV. And then the leptons are the lightest because our wave is so much smaller. So this is like f pi times f pi over mh whole square. So this is like at least 6 orders suppressed. So therefore, like the leptons are very light. So the electron is 10 to the minus 4 electron volt, muon is 10 to the minus 2 electron volt, and tau is like 10 to the minus 1 electron volt. So this is like how the sector looks like.
The QCD scale is the same in all the sectors?
It's like approximately same like when we were like analyzing the literature, it's not very far away. So it's like our QCD, like if you say it's like around 100 dish. So this is like, let's say 80 or 70. It's like 20, like with some error, it is roughly similar.
Same field content, same.
Yeah.
No, it's just, no, the quarks are lighter, so the lambda QCD is slightly different. But it's only slightly different. It's not going to be very different. Yeah, it'll be probably logarithmically set. Because your top here is very light as well, right? So, yeah.
Yeah, but that's sorry. But that is due to like the top is lighter because the wave is smaller. Yeah.
But this affects lambda QCD.
Yeah. But I think the running is not, as you said, it's not linear, but it's like more like a. Yeah.
But you're assuming the QCD coupling is the same in the UV for all these standard model circuits.
In the UV, yeah, I think so.
So if you hit different thresholds, you get different lambda QCD.
Yeah, but I think we checked that it's not like very, very different. Yeah.
So you're assuming in the UV, all the sectors have the same gauge couplings, but they have different Higgs mass? So
Yeah. So basically like it's just like copies. So everything else is the same. It's just the mh square parameter which changes. So everything else is in the n sectors. Everything else is just exact copy. You don't change anything there. We just say that the mh square is now different values. Yeah. So everything else like the same formula you can just like use. Okay. So now since we consider like this I-1 sector, so the point was that we try to use this conventional argument by Wilczek and Pisarsky that if you have 3 or more like massless quarks in your system and if it undergoes a phase transition, then it is like a first order phase transition. So in our sector, before the QCD becomes strong, all the quarks are massless because our wave is 0. So in our case, we are saying that because of the 6 massless quarks, the phase transition which happens due to the QCD is actually a first order phase transition. And if it is a first order phase transition, then we expect some kind of gravitational waves out of it. And for us, the critical temperature is around 85 MeV with some 20% error. And the percolation temperature, so this is defined as the temperature where 1/3 of the universe is in true vacuum. It lies between, let's say, 50 MeV to 85 MeV. And near the recombination, 0.3 electron volt, the exotic sector, relativistic species, they are actually the neutrinos, but the difference is like now the photons and electrons are still in an interacting path because the electron is so much lighter than the usual standard model that it doesn't go out, and photons and electrons kind of still stay in this interacting thermal path. So this is like a slightly different, and that's why the delta effective will, the bound is also slightly changed for the -1 sector.
So the can you give a very brief explanation for why the number of masses support? Why is that related to why does that determine the type of phase transition?
So I think there has been, like, in literature, there has been some arguments which prove that, like, if you have more than 3 quarks, then you have a first order phase transition. But
Can you give
I don't have a quick proof for that. I think one might have to just like go and read that. I don't have a one-line proof to.
This is the chiral phase transition?
Yeah, so our case, yeah, so it's like this went from like SU this kind of transition, right? And you basically get like a QQ bar condensate. So you just get a linear term in your potential. So that gives you a phase transition. But like to calculate whether it's the first order or second order, I'm just like using their arguments. But right now I don't have a very quick proof to give you. Yeah, and there has been like some in literature, there has also been some ambiguity because like people, I think at least some latest people claim that maybe this argument is not watertight. So I'm yeah.
This transition just in one copy, right?
No, in each of the yeah, half of the copies, like each of the yeah, but the point is like I'm not super worried about the other sectors because the energy density becomes smaller and smaller. So the gravitational waves which will come from those sectors will be even like with smaller and smaller amplitudes. So I hope to see like the gravitational wave from this sector in my interferometers and the PTAs, but I don't really expect the -2, -3, whatever to show up. So just to so the strength of the phase transition is generally expressed in terms of the alpha parameter, which is the strength of the phase transition. And this is like a rough approximate, but this is given as the delta V, which is like the potential and the free energy before and after the transition. They are divided by the total energy density of the radiation bath. So this is the alpha total. We also define a quantity called alpha -1. So here we are just taking a ratio of the delta V before and after in the transition divided by the radiation energy of the -1 sector. And ideally, we should have been able to calculate alpha -1, but we can't calculate it because the QCD is like now in a strong coupling regime. I think if you have a usual scalar field theories, then you can calculate this quantity. But in our case, we were not able to calculate it. So we just choose different phenomenological choices from literature. And the entropy production before and after the phase transition, it can be, this is like a ratio of the entropy after over the entropy before. And you can show that this is proportional to this 1 plus alpha -1 raised to r 3/4. So like for us, the important quantity is like alpha -1, which we can keep track of it. And now, as you guys pointed out, like there is always the issue of delta ineffective. So in the original model, people talked about this delta ineffective in Nnaturalness, and this was like the most important constraints that constrained the model. So for our benchmarks, we use this interacting radiation bound from CMB, and if we combine the results from Planck as well as like the shoes. So since Planck and shoes the data, there is some discrepancy. If you combine them, then this can result in the weakening of the bound. So we take it to be around 0.7. I think if you only take Planck, then it's like 0.3-ish. But if you,
BBN is 0.2.
yeah, but we are taking at CMB.
So
It's still slight. No.
0.2.
Yeah, but like if you combine like so I think we can relax by
You can't relax the BBN now with
But-
shoes.
yeah,
You're going to overproduce helium.
and you're saying
It's
is
a factor of 3 years.
but in the case of the interacting radiation, the bound is not 0.2 or 0.3, it's like 0.45-ish, just from the Planck.
0.2.
But for the interacting radiation, is that still the same? Because like our sector is slightly different, right? And like the photons and electrons are.
It's just the speed up of the expansion.
But you guys are talking about delta.
Where's the sand?
Oh, you want delta, you want N effective to change between the BBN and CMB?
Well, no,
I don't know. I mean,
I'm
it
just
can.
saying they're
You-
different.
you
There's-
They, yeah, but, his delta N effective, I assume, is coming at the weak scale. And then unless you have some way of changing it again between BBN and, or between, then you're stuck. I mean, if one delta N effective is fixed, unless you can change it.
But even like in the case of just having like this interacting radiation instead of the usual photons and like the electrons are already out, they're also like the difference is like 0.3-ish and 0.45-ish, if I remember correctly.
I mean, look, what I'm saying is because.
No, you can have. You can,
In general, yes, but in this model, how?
well, this model, I don't know, but N effective bound is, from BBN is just coming from the extra energy density that you have. It doesn't care if it's interacting or not interacting.
Okay. But even like, so, but if there is some discrepancy from which you put the bound on, like if you combine them, you still cannot make it weaker. That's the argument.
What is true, by the way? But
Oh, I think this is like supernova, it's not, yeah. And I think like there is a tension between what the Planck predicts for H0 value versus like what this guy, these guys predict. So if your like the value that you calculate has some error with this, like it's like basically like two data sets with different errors. If you combine naively, won't you expect that you can weaken the bound a bit?
I don't, but anyway. The next
In
line.
your scenario after the beginning, do you have some interpolation or the or the changing the temperature of after BBN?
Yeah, so at least like
If so, then you can say that. Then the delta BBN, delta effect BBN does not fluctuate. You can.
well, the entropy production is, yeah, but the entropy production is only happening in the phase transition of the I.
Is that before?
Less, yeah, it has to be before, right? It was like 100 MeV.
Then you should apply that. Because your delta effect doesn't change since BBN, so it should be the same.
Is the temperature of all the sectors the same?
No, like the temperature will be different, right? Because they are each in their own thermal setup, and the temperature is like just given by this.
It's possible
Ratio.
this one that's undergone transition when it does that the same. as
I don't know what
temperature now.
Delta energy, some sort of curve or something.
Not much area.
The other thing, the next line, so the proportionality constant is now going to be pretty important, right? You have the proportional.
Yeah. So the proportionality constant is just like a ratio of the different G's, the G stars. So it can help you a bit, but not.
Ratio. I don't think it's ratio of G stars, it's just a G. So,
No, I think like the way we do it is like, so different sectors have like, so you have to, well, at least like not here, but yeah, I think.
you said they're all the same. So in each of the sectors, I get a photon, and each of the sectors I have neutrinos.
Yes. Yeah, like for these guys, it won't matter, but at least for the exotic sector, it will be different.
I won't it matter?
Oh, like I mean, it's like not matter as in sense like as you are saying that the G star ratio will be like the G stars will be similar-ish, like in these sectors, at
Yeah,
least.
but for every I, I'm
Yeah.
gonna get photons and neutrinos,
Yeah,
and they're coming with a ratio of gamma I over gamma.
yeah, but this is like 1 over I-ish. This is 1 over I.
Which for I equals to 1 is 1.
Yeah, but I think like, yes, I think I should have put in like the outer factor. Yeah, I should have put in the outer factor here. Yeah, it's not like,
But I think that is actually big. That number is probably, I don't know, 4 or 5 or something.
no, I think it should not be big. Like, no, this is like a ratio of like, I'm not sure if it is big because like naively I would assume it's like a ratio of the square roots of something which is like smaller over bigger and not the other way around.
Anyway, go.
Yeah, I can check the factor, but yeah, I'm sure it's not bigger than 1. Okay. Yeah, so I think like for our exotic sectors, the delta effective -1 is basically proportional to this 1 plus alpha -1, and then gamma -1 over gamma standard model. So this is like our relevant quantity. So basically, the gamma -1 over gamma standard model is a function of m phi comma r. So that's where we will put our bounds, and we will choose different values of delta effective to put constraints, depending on some choice of alpha -1. So just to show you like the parameter space, how it looks. So on the y-axis, we have the spacing parameter r, which goes from 0 to 2.
Keep doing that.
And on the x-axis is the mass of the m5. We consider somewhere between like 0 to 300-ish. And different solid lines correspond to different choices of delta effective. So I think the most hard constraint will be from the CMB S4, which says around 0.03. So that's like the red curve. So anything above the red curve, like in future, will be excluded. And if you assume it to be like 0.7-ish, then that's like the green line. The dashed line is just the delta effective for the -1 sector. So it goes like this. And in this funnel region, there is no way that you can have constraints from the delta effective because here the mass of m5 is approximately mass of Higgs. So that's where like you dominantly decay to the SAM model. So you don't really populate the other sectors that much. And same is at this other bump. So here the m5 becomes approximately equal to 2mw of the SAM model. So you again dominantly try to decay to SAM model. So you still have some like extra space left. Yeah. And the blue region, the light blue shaded region is just when we are saying that the m5 is greater than 2 mh -1. So you can have decay to 2 on-shell like goldstones in the I less than 0 sector.
If I read this correct,
Yeah.
if R is 0.05,
Yeah.
then you can, everything is okay?
Yeah. Like if you just calculate your gamma I and if you just put in the value of.
So if you right along the bottom, R
Yeah.
is close to 0,
Yeah.
then any M5 is okay?
Yeah. Because, yeah.
Why isn't that your solution?
No, so I think what we are saying is like we are saying that there is some parameter space open, and this is like if you just look at the delta and factor constraints, and what our claim will be that you can probe extra regions from the gravitational waves.
This plot, you're supposed to be below the curves?
Yeah. So in order to be still allowed, you have to be below the lines. So the red line is like the future constraint on delta effective. Yeah. So in like once the S4 comes out, then you need to be like in this lower region.
There's essentially no constraint if R is small enough, right?
Yes. Like if R is very, very small, then you can get away with it.
And why is that? Well, how is R playing such a big role?
Well, I think like the R, if you look at,
Spacing of the masses, right?
yeah. So the way you basically MHI square, basically scaled as like some constant times 2i over R. So what it means if you make R smaller and smaller, the second guy becomes extremely heavy. So then you can't really like populate that guy. Yeah.
But do you still solve anything?
So I think the problem is like it's a delicate balance because what happens is like once you get away from delta effective, what you say is that the energy that you transfer to these sectors becomes smaller, which means that your gravitational waves, if they are produced, they also become weaker. So the problem is like your gravitational waves kind of like follow what your delta N effective is more or less. So I think the point is like to exclude these like very small values of R, you need something extra. I think you can't really use the.
No, but I'm not trying to exclude the small values of it, but do you need, R to be large to solve the little hierarchy problem? Or-
No, I think R, all values of R is possible. All you are saying is like now the spacing is different. So what you are saying is like if R is very, very like small, then basically it means that you are in this weird scenario where your one copy is sitting like at the usual 88 value, and then all the others are very tightly packed and like very close to the cutoff. So if you assume that such kind of um, partitioning is possible, then I think like there is no ambiguity within the model, but you can ask the question like, why did you choose? Like if there is a motivation of choosing the choice. So right now I'm like not really trying to answer the question of how do I get this spacing. So if somebody is wanting like trying to answer that question, I think that's where they can try to say something about whether you can exclude these values or not. But within the setup, all these values of R from 0 to 2 are like allowed.
What value of R would you have if I just put this in an extra dimension, say flat extra dimension, I have n copies of the standard model in an extra dimension? It'd be 1, right? Is that right?
So I haven't thought about that scenario, but how do yeah, I need to think. I don't see how to implement the extra dimension part in this business. Yeah, but you have to map your, like, so you'll try to map the lowest at the one, like at different contours, all the different slices of that extra dimension, right? So in a sense, you can think of, but the I should be the, like I over R should be the corresponding slices. So basically I over R should parameterize the I equal to 0 will be like the lowest slice, and then I equal to n will be the largest, but the R will, yeah. No, but R only controls like how they are spaced individually, right? But like how far you are will still depend on capital N. So like capital N will give you like what's the separation in this extra dimension, and then R will just tell you how these different slices are populated, like how equidistant they are, or how far they are from each other. So this only says like what is the difference between I plus 1 and I. That's like 1 over R approximately.
Speaking about what I've increased, say, and what's going to change?
So I think like since these guys scales as log of n, if you just increase or decrease by let's say order of magnitude, it might change a bit, but if you change it like drastically, let's if you go from tensor 4 to tensor 8-ish, then a lot more parameter space will be excluded. Yeah, log n. Yeah.
What's the shading?
Yeah, so shading is just saying that if your phi can decay to on shell h minus 1, 2h minus 1. So basically m phi is greater than 2 times mh minus 1. And then the dark blue is like if m phi is greater than 2 times mh minus 2. So in these regions, you are putting in more amount of energy density in like reasonable amount of energy density in the -1 sector. And then in this region to the -2 sector as well.
And then you also see the low reheating.
Yeah, so so I always want the reheating to happen between like the usual standard model 246, and let's say lower is somewhere above the QCD. So the point is like you want your at least the standard model copies to already be in the broken phase.
Now also with barium generation.
Yeah, so I think I am assuming that whatever saves, like, yeah, so we don't answer that problem. We assume that whatever happens in standard model kind of like whatever saves it. Yeah, so like I think like the question is like, yeah, so I think we are like not able to answer that problem because we didn't get a mechanism like to get rid of it. So if there is some like extra thing that you put in the model, then you just put it in other copies as well. But I'm not sure if how like that will work out. Like we didn't work it out. Yeah. So just to give a brief intro to the gravitational wave parameters. So basically, our gravitational waves are more or less defined when we give these 4 values of the parameters. So one alpha is the strength of the phase transition. The beta parameter gives you the time scale of the phase transition. So basically, beta is like the inverse time scale. The Tn is the nucleation temperature at which the first vacuum bubble, the true vacuum bubble, arises. And then Vw is like the bubble wall velocity. So it's like the speed of the wall of the true vacuum. So these 4 are the quantities that if you can if you know, then you can more or less say what's the gravitational wave amplitude and the frequency. So the general features for like a hidden sector like ours is basically that the the strong gravitational wave signal and then safety from an effective are kind of contrary to each other. So if you run away from the delta and effective constraints, then you basically also do not get a strong gravitational wave signal. So as an example, if your hidden sector temperature scales as TH over T standard model, you want it to be less than 1 because delta n generally scales as this guy. So you want it to be small, but then your alpha generically scales as like this chi raised to 4. So that means that if you are too far away from 1, like if it's like 10 to the minus 2 minus 3, then your basically alpha becomes extremely small, which means that your strength of the signal is very small. So you have to be in a very tight window where you still survive delta and effective constraints, but you still, and you also get appreciable strength. And the beta, for beta, if you have like larger beta, it means the transitions are very fast. But this also means that the signals are a bit weaker and they peak at higher frequency. So these like are a bit more generic statements. So if you have any hidden sector, I think this should apply. So going back to our gravitational wave signal strength. So for our case, we can show that the alpha total is proportional to alpha minus 1 times the chi minus 1 raised to 4, which is like the ratio of the minus 1 temperature over the standard model temperature. And for, if you just put in numbers, so if your alpha minus 1 is around 0.3, which is like a non-runaway scenario, I will talk about it. So then this alpha total is approximately 0.02 times delta effective over 0.7. So it's like small. And if you are in the region where your alpha minus 1 is around order 1, like 10-ish, so then your alpha total increases by an order of magnitude. So this is like more or less our strength of the gravitational waves. For the duration of the phase transition, the beta, it measures the duration of the phase transition, and it's defined as like beta over h is the derivative of the Euclidean Euclidean action with respect to the temperature at the time of phase transition. So ideally, if we could have calculated what the Euclidean action of this QCD is, then we could have calculated this guy. But I think there is not enough calculations in literature of this quantity for at least QCD-like sectors. So we then choose like different phenological choices. And there are basically some models in literature actually predict large values of beta over h, even like of the order of 1,000 or 10,000. And some predict like very small values. So we take different choices ranging from 3 to like 10 to the 4. So with respect to the gravitational wave spectrum, so there are basically like 3 different ways a gravitational wave is produced and characterized. So first is by the collision of the bubble walls. So in this contribution, only the dynamics of the phase transitioning field that matters. So it doesn't really defect too much on the background plasma. So those are from the bubble walls. The second is via the effect of the plasma. So as the gravitational wave is like moving through this plasma, it produces some sound waves, and then that corresponds to it is characterized by the sound waves. And then the third is like due to the back reaction of the fluid. So basically, if you produce some sound waves, then there is always a problem of creating some turbulent effects in the plasma. But on a general scale, the gravitational waves which are coming from turbulence is around or the order of like 1% to like 10% of the ones which are produced by sound waves. So in our study, we kind of like neglected this turbulent gravitational waves because they will be like subsumed by the gravitational waves via sound waves. But you can include them, and that will result to some 10% change. Just to define my gravitational wave density, so it's like a derivative of the energy density in the gravitational wave with respect to the log of the frequency, and it is divided by the critical energy density at that time. So this is the definition, and we use semi-analytical parameterizations to estimate our omega. So in the literature, there has been like this kind of ansatz, which works and which gives a reasonable value for the amplitude. So, and once you calculate the gravitational wave at the time of emission, then you have to redshift it by this factor r to know what the gravitational wave is today. So in our case, and basically we are summing it over. So the VW is like the ones which are coming by bubble walls, and SW is which ones comes from the sound waves. So the different factors in this formula, they are basically, there is this normalization factor. So the N corresponds to the normalization factor. So it's 1 for the bubble walls and 0.16, 0.16 for sound waves. Then the P's and the Q's are the exponents. So in this ansatz, so the P basically is the exponent of the strength of the rotational wave, and Q is the exponent of the beta, which is like the duration of the phase transition.
May I ask you something?
Yeah.
Very basic?
Yeah.
These interferential waves that are produced by the process days, right? The work.
Yeah, like the transition which results from quark
Right,
condensation.
this transition. So, I mean, after they're produced, you are in matter or radiation in the
Pardon? There? Sorry, I didn't.
I mean, you are in a radiation game, right? Yeah.
Yeah, I'm in the radiation emitted cosmology still when they are produced. Yeah. Yeah. And then I have to like redshift it by this factor R. Yeah. So for us, and then like we use this semi-analytical approximation. So the N was normalization factor, the P is the exponent for basically alpha, and Q is the exponent for beta. Then there are also suppressions due to the ball velocity, which are expressed in terms of this delta function. So this delta is the velocity suppression. It's different from for the bubble wall. For sound wave, it's approximately 1. And then there is also this spectral shape function, this S, which picks some peak frequency Fp, and F is like the value at which the gravitation was originating. So we again use some semi-analytical approximations for these guys. And also there is like once your beta becomes larger and larger, the sound wave gets an extra suppression, which I haven't like written down, but one needs to be careful, especially for beta over h of order 100 or larger, then there is extra suppression for sound waves. So basically we can earmark our region of parameter space into two distinct regions. So one is the runaway phase transition. So basically here, the idea is that the bubble walls are overcoming the friction from the plasma. So basically the velocity will keep increasing unless it hits the ultra-realistic regime. And most of the gravitational waves in this region are sourced by the bubble wall collisions. So in that summation, like the most dominant contribution just coming from the bubble walls. And here the alpha minus 1 needs to be strong just in order to beat the friction. So generally like the alpha minus 1 will be greater than 1 in this case. And as for our benchmark, so here we consider the VW to be 1 because it becomes relativistic. And alpha minus 1, we take 3 different choices. We take like 10, 5, and 1. And again for beta, we take like 1 is like small beta of 3, then 10, and then also like 1,000. So these are the 3 different benchmark scenarios that we consider for the phase transitions which are coming via the bubble walls. So the second case is like the phase transition which come via the non-runaway phase. So here basically the gravitational waves are being sourced by the sound waves. So here what happens is that the bubble wall cannot overcome the friction and it achieves a terminal velocity. And generally this is approximately VW is approximately equal to the speed of the sound CS, which is roughly 1 over root 3. And here what happens is that the expanding walls, they can produce the plasma to create a coherent motion, which in turn sources the gravitational waves via sound waves. So here the benchmark that we consider is that the coefficient for the bubble wall is 0. Even if you take it, it's like very small. And VW is 1 over root 3. And here the transition is weaker. So the alpha minus 1 is generally like upper bounded by 0.3-ish. And we take 3 values like 0.3, 0.1, and 0.05. And again, the beta over h is larger. So it's like 100 or 1,000 or even like 10,000. So these are our like benchmark scenarios. So if we put them together on the gravitational wave parameter plot, so on the y-axis is like the amplitude, and on the x-axis is the frequency in hertz. So the blue lines, the 3 blue lines here are from the gravitational waves which are sourced by bubble walls. And the yellow lines are the ones which are sourced by the sound waves. And as you can see, like even for the most extreme choice of a parameter, like if we just take alpha to be like 10 and beta to be like extremely small 3, then also we can't really go through the Voilen plots. So these green Voilen plots are the ones which are from the nanograph. So in a nutshell, even our most like promising choice of parameter space can't really explain the nanograph data fully. But the point is, like, you can still probe the different scenarios by either the upcoming facilities like LISA or the proposed ones which are like μAres in the higher frequency range. So the conclusion, the nutshell is, if the production is by the sound waves and if your strength is smaller and the transition is faster, then you will get gravitational waves which are peaked at higher frequencies. And if the transition was stronger and a bit slower, then it will be peaked towards lower frequency. And the amplitude will be slightly larger in the case of the ones which are produced by the bubble walls.
Frequency includes what primary information in your model and additional small.
Pardon?
Frequency includes what information or like what primary information in the additional small.
So I will show you how it translates to the natural parameters in the yeah, I will, in the next slide. Yeah. Just like a couple of slides. I can try to wrap it up quickly. Sorry. Yeah. So just to put the parameter to translate what we get the information gravitational wave to our parameter space. So this is our M5 versus R. On the right is just like a zoomed in version of this funnel region. So basically what we did here is that we assumed that the delta effective to be 0.7, but going from like alpha minus 1 to the alpha total, you need what the value of delta effective is, and that is correlated to the gamma minus 1. So the gamma minus 1 is a function of R and M5. So you can basically translate the bounds on the gravitational waves from different like observatories to how it will look on the M5 versus R plane. So here, as you can see, this is like the case in the runaway region. So basically, like for like some of the parameter, for some of the delta effective bounds, for at least some of the proposed experiments can probe delta effective like this R M5 versus R space better than delta effective in this funnel region. And also in some of the regions, it can be a bit better, it can beat the delta effective bounds. Especially like once the stage 4 comes, then in this funnel region, when the pi predominantly decays to standard model, you can do slightly better because then you are evading, although you are evading the delta effective and you're putting less energy, but you can still do slightly better than the delta effective bounds. But for other parameter space, delta effective is still stronger than the bounds that you get from gravitational waves. So this was like the case in which if your gravitational waves were produced in the runaway regime. I'll skip this slide, it's just like one more in the runaway. But in the case of non-runaway, again, you see that if the phase transition was a bit weaker and was a bit faster, then also you can try to probe more of this funnel region, which could not be probed by just the usual delta and effective bounds. So you do a better job, especially in the regions where you are dominantly decaying to the standard model, either via the mass is proportion like very close to the standard model Higgs or close to 2 times MW. So just to conclude, so this Nnaturalness, it addresses the small hierarchy puzzle, which is associated with the Higgs mass by invoking n copies of standard model. And in our study, we try to understand more about this first electrostatic sector, which undergoes a QCD phase transition. And the gravitational waves in this region are predicted to be between, let's say, a nanohertz to millihertz frequency. And by itself, it cannot explain this recent observation of the stochastic gravitational waves background by the nanograph, but a large parameter space of the Nnaturalness can be probed by future PT experiments, as well as like the other planned and proposed observatories like LISA, BBO, or even like μAres. So yeah, so this is what I had. Thank you.
Oh, shit. Try to read the last one.
What's the value of this little a?
Pardon?
What's the value of this little a?
Yeah, so it has to be like upper bounded by lambda h over n, but it can be smaller. So it's like roughly, if I say less than, I think like a over m5 will be less than 1. Like I will take a over m5 to be less than 1. So a is dimension full, so I will take a over m5 to be less than 1.
one thing is the decay of the input of one, and the other thing is when you thermalize the standard model,
Yeah.
there is stuff between standard model and other sectors to an offshore line.
Yes.
And that is a different process before a higher than A, but you have more kind of time to relax, right? So make sure that the cross is slow on the expansion. Fully thermalized.
Yeah. Yeah. So I think as long as I keep A over M5 to be much less than 1, because it's just like upper bounded by. Yeah, so I think it is free, like at least in my story, I can take it to be like not 0, but like I can take it to be small. So I can just have some kappa factors like -2, -10 to -3-ish.
Not 0, but small.
Yeah, but there is like no lower bound per se.
But you should be able to estimate it very easily, right? If you're thinking of HH to HH with phi exchange.
Yeah.
Right? That's what, right? So, you know, that cross section you can compute.
Yeah, so I think from there only, I think you get like this lambda h over n, this upper limit is that's where it comes from. So as long as it's like smaller than this, like lambda h, A is like less than lambda h over n, I think you don't like that the talking is small. I think that was like the like we do the computation.
So what n comes.
By the way, that these models are not compatible, right?
No. Well, the big gauge groups, SU 2500, SU 50,000.
If you unify this, there would be then loop corrections to the mass of phi.
Yeah, I haven't thought about like unifying it, but I don't know how you think about like I haven't thought about that.
Oh, okay. SU5. SU5 to the pendulum.
I get it.
Yeah.
If you assume delta smaller than 0.7,
Yeah.
I mean, in this figure, this figure you add with the power spectrum, the gravitational wave spectrum, the spectrum goes down, right?
Yeah, so if my delta N effective becomes smaller, basically my alpha minus, like the alpha total also becomes smaller. Yeah, it becomes like the amplitude will reduce. So it will just like scale down.
A lot, right?
No, yeah, I mean, it depends how much I'm changing this. Like if I only change by order of magnitude, yeah, maybe an order of magnitude-ish, because like linearly related.
And another thing, I mean, you decide that, okay, the half of the copies have negative mass and the half.
I think that will happen naturally just by the I going from like -n/2 to +n/2. So if you just take, because like the formula was like 2i over r plus 1.
Statistically, you expect
Yeah. If you assume that distribution is correct, then
distribution you keep in mind, right?
yeah. So like naively, I assume like a linear-ish kind of
Linear
distribution.
7 of 0.
Yeah, but it will pass through 0. Like if I assume, like I can like, so in order to have some, I mean, like, so if I have to explain any other kind of distribution.
Why does it go from minus
Yeah,
5,000 to plus 5,000?
Exactly.
Not 0 to 10,000
Yeah.
or
Well, other
minus 10 to
Yeah.
plus 9,990.
And also, you have also uniform distribution. Maybe it's not equal, right? Something very.
Yeah, I mean, like, so as long as I have like one negative sector, I should be fine. But yeah, if I don't have one negative sector, then like, yeah, I can't. I mean, like, you still get bounds from delta effective, but I won't have any gravitational waves coming in. Like the delta effective bounds will always be there, no matter how you distribute it. Yeah.
One big question. I think you have very many species here.
Yeah.
So this will greatly affect renormalization of gravitational interaction. So that the scale at which your gravitational interaction becomes strongly coupled will be greatly affected here. Right? So can you make some comments on that? I think in the original paper there were some comments on that. Comments on this point. I don't remember. So can you?
Yeah.
Yeah. So he will answer.
Yeah, I don't exactly remember, but I think I think the way like the A goes, like the scaling of the A can help to ease it out. Because there is also like 1/n always coming in the A. That might help it out, but I'm not exactly sure if I remember that argument.
I think the scale at which your gravitational interaction becomes strongly coupled will drastically decrease. Because its scale is, I think, skirt inward.
Yeah.
So that, I'm asking,
It doesn't take the extreme value of it. It's just 10⁴, right? So the scale would be reduced by a factor of 100. So this is not, GEA had the model of 10⁻30 copies, right? And then, yes,
here I see. Okay.
this is, and natural is done in the race. Right?
Thank you.
Yeah, you can just leave.